We are discussing the CSIR NET Physical Science December 2014 Quantum Mechanics problem. This is a 3.5 marks MCQ. Let us read the statement of this problem. Suppose Hamiltonian of a conservative system in a classical mechanics is H is equals to omega xp, where omega is a constant and x and p are the position and momentum respectively. The corresponding Hamiltonian in quantum mechanics in the coordinate representation is. So we have to write it down, the wave function in quantum mechanics. Operator, its corresponding operator in quantum mechanics. Solution. We have H is equals to omega xp, where x, p are classical, dynamical, variable, and every classical, dynamic operator has its corresponding operator in quantum mechanics. That is, x is replaced with x and p changes to pk, that is minus ih cross del by del x. Since xp do not commute in quantum mechanics, the classical operator must be symmetrized so that xp and px becomes identical. That is, h is equals to omega by 2 xp plus px implies h psi would be equals to omega by 2 xp psi plus px psi. This can be written as h psi is equals to omega by 2 into x minus ih cross del psi by del x plus minus ih cross del by del x into x psi, which can be written as omega by 2 minus ih cross x del psi by del x plus minus ih cross x del psi by del x plus minus ih cross psi. So h psi further can become omega by 2 minus ih cross 2x del psi by del x plus minus ih cross psi. So we can take it minus ih cross outside omega and take it 2x by 2 del by del x plus 1 by 2 psi minus I h cut omega x del by del x plus half psi h psi. Thus, operator H in quantum mechanics takes the form equals to minus I h cut omega x del by del x plus half. Let psi1 and psi2 denote the normalized eigenstate of a particle with energy eigenvalue E1 and E2 respectively. With E2 greater than E1 at time t is equals to 0, the particle is prepared in a state psi t is equals to 0 1 by root 2 psi1 plus psi2. This is the shortest time t at which psi t equals to t will be orthogonal to psi t is equals to 0 is. Solution. We have wave function of the particle at t is equals to 0 is psi 0 equals to 1 by root 2 psi 1 plus psi 2. The wave function of the particle after time t is psi t is equals to 1 by root 2 psi 1 e to the power minus I e1 h t by h cut plus psi 2 minus I e2 t by h cut. Applying condition of orthogonality, we get psi 0 equals to psi of t equals to 0 implies 1 by 2 equals to e to the power minus I e1 t by h cut e to the power minus I e2 t by h cut is equals to 0 implies e to the power minus I e1 t by h cut equals to e to the power minus I e2 t by h cut implies e to the power I e2 minus e1 t by h cut equals to minus 1. This or e to the power minus I e to the power e2 minus e1 t by h cut is equals to e to the power I pi implies I e2 minus e1 by h cut t is equals to I pi. I to I cancel. T would be the minimum time after which psi T is equals to T become orthogonal. Psi T is equals to 0 is, that is T is equals to pi h cut by A2 minus A1. Thus, our correct answer for this problem would be option B. Consider the normalized wave function phi is equals to A1 psi 11 plus A2 psi 10 and A3 psi 1 minus 1, where psi Lm is simultaneous normalized eigenfunction of the angular momentum operator L square Lz with eigenvalue L plus 1, H square and mh cross respectively. If phi is an eigenfunction of the operator Lx with the eigenvalue h, then we have to determine under one values on A1 and A3, this wave function become eigenfunction of operator Lx. Now, solution. We have phi is equals to A1 psi 11 plus A2 psi 10 plus A3 psi 1 minus 1, where psi Lm are simultaneous eigenfunction of the angular momentum operator and Lz with eigenvalues L plus 1 h cross square and ml h cross respectively. The operator Lx is in terms of ladder operator is defined as Lx is equals to 1 by 2 plus L minus. Applying wave function psi operator Lx, we get Lx phi is equals to 1 by 2 L plus phi plus 1 by 2 L minus phi is equals to 1 by 2 L plus A1 psi 11 plus A2 psi 10 plus A3 1 minus 1 plus 1 by 2 L minus A1 psi 11 plus A2 psi 10 plus A3 psi 1 minus 1. This term would be equals to Lx phi 1 by 2 h cross A2 root 2 psi 11 plus A3 root 2 psi 1 0 plus 1 by 2 h cut A1 root 2 psi 1 0 plus A2 root 2 plus 1. That is equals to 1 by 2 h cut a2 root 2 psi 1 1 plus a3 root 2 plus a1 root 2 psi 1 0 plus a2 root 2 psi 1 minus 1 lx 5 plus 2 h cross a1 psi 1 1 plus a2 psi 1 0 plus a3 psi 1 minus 1. Now, where we have used a1 would be equal to a2 by root 2, a2 would be 1 by 2 a3 root 2 plus a1 root 2 and a3 is equals to a2 by root 2. These conditions are satisfied. These conditions are satisfied for a1 and a3 is equals to 1 by 2 and a2 is equals to 1 by root 2. Thus our option would be, so option B is our correct answer. Let x and p denote respectively the coordinate and momentum operator satisfying the canonical commutator relation x p is equals to y in natural unit h cross is equals to 1. Then the commutator x p e to the power minus p is. Solution. We have x p e to the power minus p. We use here the standard identity for commutator relation x gp equals to I h cross dgp by dp. Applying this identity on giving commutator, we get x p e to the power minus p is equals to I h cross del by del p. P e to the power minus p is equals to I h cross e to the power minus p e to the power minus p is equals to I h cross 1 minus p e to the power minus p. The value of commutator x p e to the power minus p in natural unit of h cross equals to 1 is x p e to the power minus p equals to I 1 minus p e to the power minus p. Thus, our answer for this problem becomes option A. Let sigma, which is in closed term sigma 1, sigma 2, sigma 3, where sigma 1, sigma 2, sigma 3 are the Polish matrix. If vector A and B are the two arbitrary constant vectors in 3 dimensions, the commutator A dot sigma and B dot sigma is equal to, in the following identity, in the following, I is the identity matrix. So, solution. We have commutator A dot sigma into B dot sigma can be written as A dot sigma to B dot sigma minus B dot sigma into A dot sigma, where we know it sigma equals to sigma 1, sigma 2, sigma 3 are Polish matrices. Sigma 2 and sigma 3 Polish matrix. Now we use a standard identity for commutator relation. That is A dot sigma into B dot sigma is equals to A dot B plus I sigma dot A cross B. Similarly, B dot sigma into A dot sigma would be B dot A plus I sigma dot B cross A. Substituting these values in the expression of commutator, we get A sigma into B dot sigma equals to A dot sigma to B dot sigma minus B dot sigma to A dot sigma. This term would be A dot B plus I sigma into A cross B minus B dot A plus I into sigma B cross A. So this result would be equals to twice I sigma A cross B, where we have used A dot B is equals to B dot A and B cross A equals to minus A cross B. Thus, our option for this problem is option B. The ground state energy of the attractive delta function potential is Vx is equals to minus B delta x, where B is greater than equals to 0, is calculated with the variational trial function psi x is equals to a cos pi x to a for minus a x less than a 0 otherwise. So we have to determine the ground state energy. Solution. We have psi of x is equals to a cos pi x by 2a in the range minus x less than a 0 otherwise. The normalization constant is obtained from the normalization condition that is psi of psi equals to 1 implies a square minus a to a cos square x by 2a dx equals to 1 implies a square a equals to 1 implies a equals to 1 by root a. The normalized wave function is given by psi of x is equals to 1 by root a cos pi x by 2a in the region minus a x less than a, where is the normalization parameter. The Hamiltonian for the system is h cap is equals to minus h square by twice m d square by dx square b into delta x. The energy from this Hamiltonian is given by E is equals to psi of x h psi of x equals to psi of x minus h square by twice m square by dx square minus b del x psi of x equals to minus h square by twice m psi of x to del square psi of x into dx square minus b psi of x delta x into psi of x. Let us evaluate the value of each of these inner product separately. So the value of first term of inner product is psi del square psi x by dx square equals to psi minus pi square by 4a square into psi of x equals to minus pi square by 4a square psi of x into psi of x equals to minus pi square by 4a square. Similarly, the value of second term of inner product is, that is psi of x delta x into psi of x, which is equals to 1 by a minus a to a cos square pi x by 2a delta x into dx, which is turned out to be 1 by a, where we have used property delta x fx dx equals to f0. Substituting these values in the expression of energy, we get E of A is equals to h cross square pi square by 8m square minus b by a. Now the value of variation parameter A is obtained by differentiating EA with respect to A, that is del E by dA equals to minus 2 pi square h square by 8ma cube minus b by a square equals to 0 implies a equals to h cross square pi square by 4mb. Substituting the value of A in EA to obtain ground state energy, as E would be pi square h square by 8m into pi square h square by 4m p square minus b by minus b by pi square h square by 4mb. So this would give us 2mb square by pi square h square minus 4mb square by pi square h square, which is equals to minus 2mb square by pi square h square. Thus, the correct answer for this problem would be option B, minus 2mb square pi square h square. Let psi is a linear combination of C0 and state 0 plus C1 and state 1, where C0 and C1 are constant with C0 square plus C1 square equals to 1. Be a linear combination of wave function of the ground and first excited state of the one-dimensional harmonic oscillator. For what value of C0 is the expectation value of average x is maximum? So we have to determine the value of 0 at which average x become maximum. And what is the maximum value of average x? Solution. We have psi is equals to C0 0 plus C1 state 1, where psi dot psi is equals to C0 square 0 0 plus C1 square 1 comma 1 is equals to 1. This implies C0 square plus C1 square equals to 1, or C1 square would be 1 minus C0 square. Now, the expectation value of average x is given by del x is equals to psi x psi, which can be written at C0 square 0x0 plus C1 square 1x1 plus C1 C0 1x0 plus C0 C1 0x1. Now, we are using the standard result of harmonic oscillator, that is mxn will be equals to root over h cross y twice m omega root n plus 1 delta m into n plus 1 plus root n and delta m into n minus 1. So, let us determine the value of each of these inner products. That is 0x 0 will be 0. Similarly, 1x1 is also 0. However, 0 x1 will be equals to h cross by twice m omega into root 1 delta 0 comma 0. So this value will be h cross by twice m omega. Similarly, one x0 will be root over h cross by twice m omega. Here delta 1 into 0 plus 1, and here you would be having 0 plus 1. So this gives us h cross by twice m omega. Now inserting these values in the expression of average x, we get x will be twice C0 C1 to h cross by 2 m omega, which can be written 2 C0 1 minus C0 square into h cross by twice m omega. To obtain maximum value, this slope of above equation must be 0. That is del x by dc0 would be equal to d by dc0 into 2c0 1 minus c0 square h cut by twice m omega equals to 0, implies 1 minus c0 square minus c0 square by 1 minus c0 square is equals to 0, implies 1 minus c0 square minus c0 square is equals to 0, implies c0 is equals to 1 by root 2. The maximum average x becomes average x is equals to 2c0 c1, or I would be writing in terms of 1 minus c0 square into root over h cross by twice m omega. So 2 1 by root 2 1 minus 1 by 2 into root over h cross by twice m omega equals to root over h cross by twice m omega. Thus our answer for this problem would be option C. Consider a particle of mass m in the potential Vx is equals to A mod x. The energy eigenvalue En for n0, 1, 2, 3 in the WKB approximation are. So we have to determine what is the dependence on energy using WKB approximation. Solution. Classical energy for a particle is given by E is equals to P square by 2m plus Vx, expressing the momentum as function of energy. We get P is equals to root over twice m E minus A mod x power 1 by 2. The turning point for the particle are obtained when energy of the particle become equal to its potential energy, that is E is equals to V of x equals to A mod x, implies x is equals to plus minus E by A, implies x minimum minus E by A and x maximum equals to E by A. The value left hand integral in Bohr-Sommerfeld quantization rule is P dx is equals to x min to x max equals to twice m A E minus A mod x to dx, which can be written as 2 root 2m 0 E by A root over E minus A x into dx. This can be written as minus root 2 by m 4 by 3a E minus ax की power 3 by 2, limit 0 to E by A, which gives us root 2m into 4 by 3a e to the power 3 by 2. Next, but from Bohr-Sommerfeld quantization condition, we have P dx is equals to n plus 1 by 2 pi h cross. Substituting the value of integral in above equation we get root 2m 4 by 3a e to the power 3 by 2 n plus half pi h cut implies e to the power 3 by 2 n plus half pi h cut by root 2m into 3a by 4, or it would be 3 by 4 a pi h cross root 2m plus 1 by 2 की power 2 by 3. Now the question is, do we need to solve this problem using such a tedious method? The answer is obviously not. Here I am writing standard result. Shortcut for potential of the form Vx is equals to lambda x to the power n m En is proportional to lambda 2 into m plus 2 and n plus half the power 2m divided by m plus 2. So that is the dependent over m. For potential Vx is equals to a mod x, m is 1. So here En is proportional to lambda की power 2 by 3 into n plus half की power 2 by 3. So n plus half की power 2 by 3 we can check it up, is given only in this option. So without solving it, option B is our correct answer. The Hamiltonian H0 for a three-state quantum system is given by the matrix H0 is equals to 1 0 0 0 2 0 0 0 2. When perturbed by a Hamiltonian this, where epsilon is less than 1, the resulting shift in the energy eigenvalue E0 equals to 2. So first, this problem is related with the time independent degenerate perturbation. We have H0 is equals to 1 0 0 0 2 0 0 0 2 and H dash as 0 epsilon 0 epsilon 0 epsilon epsilon 0. The eigenvalue and its corresponding eigenfunction for unperturbed Hamiltonian is given by eigenvalue equals to 1, corresponding wave function phi 3 would be 1 0 0. Eigenvalue 2 would be 2, phi 2 equals to 0 1 0 and eigenvalue E1 is equals to 2, phi 1 and eigenfunction is 0 0 1. We can check it out. E2 2 E1 and E2 are having same eigenvalue but different eigenfunction. So let us write down perturbed Hamiltonian for the eigenstate phi1 and phi2, that is HP would be equals to phi1 H dash phi1, phi1 H dash phi2, phi2 H dash phi1, phi2 H dash phi2. Let us determine the values of each of the inner product given in the matrix as. So first we are determining phi1 H dash phi1. So phi1 would be 0, 1, H dash 0, epsilon 0, epsilon 0, epsilon 0, epsilon 0 into 0, 0, 1 resulted into 0, 0, 1, 0, epsilon 0 equals to 0. Similarly, phi2 H dash phi2 will be 0, 1, 0, 0, epsilon 0, epsilon 0, epsilon 0, epsilon 0 into 0, 0, 1, 0 equals to 0, 1, 0, epsilon 0, epsilon equals to 0. Now, phi 1 H dash phi 2. This term is phi 2 is equals to 0, 1, 0. Sorry, phi 1 is 0, 1, 0, epsilon 0, epsilon 0, epsilon 0 equals to 0, 1, 0. Give us 0, 0, 1. Give us 0, 0, epsilon equals to epsilon. Similarly, phi 2 H dash phi 1 equals to 0, 1, 0, 0, epsilon 0, epsilon 0, epsilon 0, epsilon 0, 0, 0, 1 equals to 0, 1, 0, 0, epsilon 0 equals to epsilon. Substituting these values in perturbed Hamiltonian, HP, we get HP is equals to 0 epsilon 0. The eigen values of HP is given by the circular equation, that is H minus lambda I is equals to minus lambda epsilon minus lambda equals to lambda square minus epsilon square equals to 0, implies lambda is equals to plus minus epsilon. Thus, the energy of perturbed of energy level the energy E0 equals to 2 after perturbation changes to 2 plus minus epsilon. So degenerate perturbation, remove degeneracy in the energy eigenstate. So our answer is C for this problem. The effective spin-spin interaction between electron spin Sc and the proton spin Sp in the ground state of the hydrogen atom is given by H dash is equals to A Sc dot Sp. As a result of this interaction, the energy level is split by an amount. So we have to determine the splits or separation in the energy levels. Solution: we have H dash is equals to A Sc dot Sp. The total spin of the system is given by is equals to Sc plus Sp implies S square equals to Sc square plus Sp square plus 2 Sc dot Sp, or this give us Sc dot Sp is equals to 1 by 2 of S square minus Sc minus Sp square. Substituting, thus our Hamiltonian takes the form H dash is equals to A Sc dot Sp is equals to A by 2 into S square minus Sc square minus Sp square. The energy of this system is given by, that is E would be equals to A by 2 H cross square S into S plus 1 minus SC into SC plus 1 minus SP into SP plus 1, where we have used S square S comma SZ is equals to H square S into S plus 1 comma S into SZ. SE square SC into SZE would be equals to H cross square SC into SC plus 1 into SC into SZE, and SP square will be equals to SP SZP equals to H cross square SP into SP plus 1 to SP into SZP. The energy for singlet state S is equals to 0 is E S is equals to 0 equals to A by 2 to 0 minus 1 by 2 into 1 by 2 plus 1 minus 1 by 2 into 1 by 2 plus 1 equals to minus 3 by 4 A H cross square, where we have used S is equals to 0, C equals to SP equals to 1 by 2. The energy for triplet state is equals to 1 is E S is equals to 1 equals to A H cross square by 2 into 1 plus 1 minus 1 by 2 1 by 2 plus 1 minus 1 by 2 into plus 1 equals to 1 by 4 A H cross square, where we have used S is equals to 1 equals to SP equals to 1 by 2. The energy difference between two states is delta E is equals to 1 by 4 A H cross square minus 3 by 4 A H cross square equals to A H cross square. So, our answer for this problem would be option C.